this video, we would be talking about the mathematics of general relativity. However, I would like to tell that the topics that we would be talking today are very, very important for any student who is learning physics or mathematics. These topics are super important, very central to the building the basic foundation of physics and mathematics. I would request you, either you are learning general relativity or not, that doesn't matter, but these components for today's video are extremely important, and I would request the viewers not to skip but watch this entire video, because this would help you through simple concepts, illustrations and understanding to build up the basic foundation of physics. My name is Shaunak and you're watching this video on my channel Physics for Students. A warm welcome to the second part of this series of video, the mathematics of general relativity. So first, as we used to do, let us first look into what the topics we are covering. So we would first start with vectors and basis of vectors, what are called vector fields, what is the gradient of a scalar field, divergence of a vector field, index notation, and finally Einstein's summation convention. First, we would start with vectors and bases of vectors. Now, the formal definition of a vector is something that it is an element of a vector space. Basically, if you have a group of things which you can add and subtract or multiply by an ordinary number and still end up with another thing of the same type, then those things are called vectors. Simply, vectors can be used to represent physical quantities with magnitude and direction, such as velocity or force. We can physically draw these vectors as directed line segments aligned with an arrow. A wind map, for example, uses a lot of little arrows. This figure, which shows that a person travels walking at a constant speed. He first walks at 4 km due north and then takes a right turn towards 3 km east, and this motion is represented by vector A, which is 4 units long, vector B, which is 3 units long, and joining of the tail A to B form the vector C. So what we can tell is that if we measure the length of C, that is the directed line segment, the length of a vector is known as magnitude. So using the usual way of adding the vector, we can say A plus B equals to C, and using Pythagoras' theorem, we can calculate length of a vector, which is known as magnitude, as C equals to 5. Okay, in this convention, we would be using two ways of mentioning the vector. One is the vector with an arrow on the top, another is bold. However, to avoid confusion, I would be using bold typeface so that it becomes easier. In contrast to vector quantities such as velocity, there are also things which are called scalar quantities, which have magnitude but no direction. Speed is an example of a scalar quantity, referring only how fast an object is moving. Velocity, as we have seen, is a vector quantity that refers not only how fast something is moving, but in which direction it is moving. Now, this refers to how fast an object is moving. So a vector consists of the product of its components and objects known as basis vectors. Now, basis vectors, the way we define, it has two ways of defining. One is that in 2 dimensions we need 2 basis vectors, and in 3 dimensions we need 3 basis vectors. Let us think of a Cartesian coordinate. Okay, so the same vector can be represented in different bases. For example, this blue and the red arrow shows that the same basis vector, how it has been represented. So in a Cartesian coordinate, this is a 3-dimensional vector V, which consists of products of its components. So you get Vx, Vy, Vz along with a set of basis vectors Ex, Ey and Ez. I put a little bit of hat on the top just to mean that these are 1 unit long and pointing around X and Y and Z axis, right? So this is the basis vectors, and we can write it in this way. Note that the subscripts X, Y and Z are basically allow us to identify the 3 components, and the magnitude V, that is the distance from the center to the red dot which is being used, the magnitude can be calculated using this Pythagoras' theorem. Okay, in particular, there is a useful type of vector which is called the position vector. This blue one, which is a radius vector, we can call it a radius vector R, which is right from the origin, which is used to define the position of a particle, which is this one, P. The position of a vector magnitude is also used by this R, and we can calculate this. Sometimes we use a unit radial vector, which is simply a radius of the vector. Now there are several ways of multiplying vectors. The two most common things are called cross product and dot product. Here I would like to take a pause. If you really want to know deep into cross product and dot product, I have made a very lengthy and a detailed video on what is cross product, what is dot product, how it is important to industry. You can just go to my channel Physics for Students and check it out. Now we are interested in the scalar product, which actually gives the Cartesian component of two vectors. So this would be equal to A dot B, which is the x component of A with B component, x component of B, followed by y component of A and y component of B, and so on. Okay, so you will often see that the same equation, the Newton's second law, F equals to ma, is often written where force is vector and A is the acceleration vector. But because F and A are vectors, they can be broken down into respective components, which we just learned, and this can be equals to f of x and f y component of force and z component of force. So sometimes we are interested in the direction, so this is something which breaks up the F equals to ma, the force part, into three different ways. Okay, so Newton's second law, we know F equals to ma, and equating with the momentum, mass times velocity, can be also written as this, and this. I have shown this in my previous video, how Newton's second law is used using the derivative. Now we can use also in this way, right? It can be used as a scalar equation. That is why there is no bolt, no arrow. Okay, so we come to the next part, which is called the vector fields. Okay, I would like to request you to imagine this as a room. Forget the coordinates, forget the numbers also. Imagine that is a room filled with moving air. The air might have faster near an open window or above a hot radiator or slower in corners. This can also be imagined. So we would measure the velocity of the air at every point in the room, and we would express that velocity in terms of x, y, and z. So air might be moving faster near an open window, slower, etc. So we would measure the velocity of the air at every point of the room. So velocity, as it is expressed in x, y, and z, we can write it in this way, right? V equals to v x, y, z, then v of x followed by e hat x and v of y in this way. What does this actually means? It means that this v is a function of x, y, z. Specifically, if I talk, then the components of vx, vy, and vz are also each are functions of x, y, and z. So what we have done is that we have described what is a vector field. That means every point in the room has a vector associated with it, and it tells us the speed and the direction, whatever we want to calculate. So this is something very central. What are vector fields? We just calculate it by breaking up the components, and we define it so that we can measure the velocity. Okay. Now we want to define a vector. Quite easy. So if a vector field on 2 or 3 dimension space is a function f that assigns at each point x, y or x, y, z for 2 or 3 dimensional given by f of x or f of x, y, z. So in vector calculus, this is very important because it points to each subset in space. Just I gave an example that for an instance, a vector field in the plane can be visualized by collection of arrows. You see these arrows are going each attached to a plane. And vector fields are often used to model, for example, the speed and direction of a moving fluid or the strength and direction of some force. So here you can see that we would like to take an example, and we would like to plot and see how actually vector fields behave. Now I would like to just take a hypothetical function. This is just a hypothetical function 2y plus x plus 3z. It doesn't have any relevance to this. and I assume the position of x to be 1, y to be 2, and z to be 3. And what I am doing in the third line is that I'm just substituting those values of x, y, and z in my function. And what I get is this. So if I get, that means I get the ex component to be 2, y component to be 14, z component to be. So that means I'm getting a quadrant, right? I'm getting a value through which I can find either the velocity, the fluid, the wind speed, whatever. If you put the position x equal to z, x equal to all of them 0, then we get v equals to 0, which can be interpreted as the velocity of air equals to 0. And where it will be around this region, where almost x, y, and z comes to 0. So finally, we can summarize that we have created a function and through which we can calculate the vector field. So I hope this is quite clear, right? So this is how vector fields are calculated. It is a kind of a function. We have shown it, and then we plug in the value and we get whatever we require in order to calculate it. Okay. Now we come what is called the gradient of a scalar field. Okay. I will like to first show what the gradient operator looks like. So I have taken the Gauss's laws example. So the differential form of Faraday's law, Ampere-Maxwell's law, all uses this operator, right? All are using this nabla operator. Okay, so what we get from here is this del operator. It takes derivatives. So you can calculate a curl of a vector with a multiplication sign. So it shows the curl of a vector. We can calculate divergence of a vector using a dot product. This is the divergence. We can even calculate the gradient, which we are right now going to do, and we can also we can calculate what is called the Laplacian, which we will also see. So the nabla symbol is basically what we call as the differential operator. So gradient of a scale in simple language it defines a vector field, the magnitude, which is equal to the maximum rate of change. Now it can be steep, it can be something, but it actually shows the maximum rate of change and direction of which it is the same displacement. So gradient of a scalar field is a field whose magnitude is the rate of change which points, right? So we get something like this. This is the differential operator, which gives through calculus the differentiation, and a differential operator is an operation defined as a function of the differentiation operator. And here we get it. So del by del x, these are all partial derivatives, right? Del by del y. So only this has the differential operator is used as to calculate. We have seen divergence, gradient, and curl, but we are only interested in curl, but we are not interested in curl, but we are looking into the gradient of this in this section and divergence that we would soon see. So this one, nabla phi, is the scalar field, and we find it as an important vector field known as the gradient of grad, which is denoted by this. Okay, so now what we will do is that we will hypothetically take, for example, assume that the air temperature T varies at a room from point to point inside a room. Now the temperature may be higher near a radiator, for example, or colder near an open window, whatever it is. Now say we describe the position of any point in the room using 3 Cartesian coordinates T of x, y, and z. Whatever be the measurement, it can be meters, centimeters, we are not worried. Now assume that we have worked out an equation that gives the temperature for any point x, y, and z, right? And function also. So T is just a number, and it is an example of a scalar field. And this Greek letter phi is used to indicate a scalar field. Now in ordinary Euclidean space, for a point in a scalar field phi, right, the gradient in a vector that points is the greatest increase of phi. So here it is the greatest increase of phi, nabla phi equal to del phi by del x, followed by the x component, then del phi by del y, followed by the y component, del phi by del z, followed by the z component. Or we can also write in this way, right? So what is happening out here is that the gradient of a scalar field is ultimately a vector field. So we try to find out hypothetically by posing a T as the temperature, right? And then getting to the equation that gives us any temperature, and then we took phi as a scalar field or a point in scalar field, and then using the normal Cartesian coordinate, we did the partial derivatives and we found out that this details. So the gradient magnitude of the gradient tells us how fast phi is changing in whatever direction or how fast things are moving. Okay, now the next concept from phi, as I told, that with the gradient of a scalar, we need to move to divergence. Now divergence in vector calculus is a vector operator that operates on a vector field producing a scalar field, giving the quantity of the vector field source at each point. More technically, we can call the divergence represent the volume density of the outward flux of a vector field from an infinitesimal volume around a given point. It is taken from these two Latin words, dis and urger, and in physical terms, we can say that it measures the outgoingness. As you see from the red dot point, it shows the outgoingness, the extent to which there are more fields of vector. So it was actually, if you go back to my history of Maxwell's equation, you will see that I have shown in details that it was James Clerk Maxwell who originally coined the term convergence in his thesis paper, and then it was Oliver Heaviside who later coined the term divergence. So we have got a positive divergence, we have a negative divergence, and we have got a zero divergence. So this is a kind of a basic idea of what is a divergence. Okay, so positive divergence is where things are spreading out and del dot v would be greater than 0, and it looks something like this. So it actually spreads out x0, y0, and where the value is at some point is greater than 0, at some point x0 is greater than 0. This is positive divergence when it comes out to be positive. So we can say that the fluid or anything which is flowing around the vector field becomes less dense around. Why? Because this is spreading. So we get a zero divergence also when things are going up and going down. Here you see that it is whatever is coming in, it is coming out. So at some point the fluid flows freely, but the density remains constant. The density will be constant, but the fluid will be flowing freely. For example, incompressible fluids, when it comes out to be 0. And we have got what is called, okay, negative, we have seen that. Okay, so for a Cartesian vector field, for example this one, what we can say is that the divergence is given by this, very simple, and if v is the gradient of a scalar field, that means v is equals to nabla phi, then this comes out where this is true, right? So you see that these signs, I would say nabla square, and this is actually what is called the Laplacian or the Laplace operator, which tells us the divergence of the scalar field. So this actually tells out the divergence of the scalar field. So we move to the next page and we find these two are basically the Laplace operator. Our Laplacian is a differential operator given by the divergence in a Euclidean space. This famous person, Pierre-Simon Laplace, founded this equation and pioneered the Laplace formation, which appears in many branches of science. Don't worry, if you want, I can make a separate video on Laplacian transformation Laplace operator. It is very important to any part of physics and mathematics. Okay, now we come to what we call is an Einstein summation convention. Now, before going into Einstein summation convention, I would again go back to the examples that I have taken and I would like to show. So what I would like to show is that in Cartesian coordinates, a three-dimensional vector, for example V, consists of the components Vx, Vy and Vz plus a set of basis vectors which are Ex, Ey, Ez, each of which points along the direction of the coordinate axis, and this can be written as this, right? So the X, Y and Z subscripts, which you can see I have marked it in red, are indices, allowing us to identify the three components of V sub X, V sub Y and V sub Z. Similarly, this X, Y, Z subscripts let us identify the basis vectors E sub X, E sub Y and E sub Z. In a more clear manner, we can always write like this, right? V sub I, E sub I, and where the index value of I can take something between 1, 2 and 3 for 3 dimension Let us assume for the time being, right? So it can take. So the components of V can be written as Vx equal to V1, Vy equal to V2, and so on. And the basis vectors obviously can be written as this: Ex equal to E1, Ey is equal to E1, E2, and E3, and so on, right? So that is how it is written. So in other words, we can say this: P equals to V sub I, E sub I equals to V1, E1 plus V2, E2 plus V3, E3, which will be equals to this one, Vx, Ex, and this one. Now, this expression is something which is called the index notation. Now, there is definitely a kind of a use of index notation. So, it actually helps us to write complicated expressions in a much more coincised manner. So, this is something which is basically, we are coming to Einstein notation convention. Now, before that, this Einstein notation summation convention is something which deals with two types of vectors, which results into two types of tensors. I have explained these two concepts in very details in my video in metric tensor. You can go to my playlist in general relativity. You can find out metric tensor. However, we would just like to tell that currently there are two indices which just changes or identifies the vector. The covariant has got lower indices and contravariant have got upper indices, right? But both co and contra are vectors consist of components. Now, the Einstein summation convention means that when an index occurs twice in the same expression, that expression is implicitly summed over. For example, this one, right? So it is 1, 1, 2, 2, 3, 3, and we can sum it and write it as y equals to ci and xi. Once we will do with more with tensors, this summation convention, etc., will become clear. Now, one thing is very important is that when you look into this expression, do not take x to the power 2 or x squared as an exponent. It is the second component of x. And this xi is basically an index which occurs in an upper superscript and once in lower subscript position in a term. This is a very common misconception that it is x squared. No, it is not x squared. It is the second component of x. And in general relativity, we have a common convention, which is these two. The Greek alphabet are used for space-time components like nu, etc. And the Latin alphabet, I, J, etc. are used for spatial components, but indices take on value something. So this is something important. It is not an exponent, it is the second component, and we use Greek alphabet in GR to denote the space and time components and the Latin alphabet spatial components. Okay, we have seen that the scalar product of the vector is given by something like this, right? So in index notation, obviously we can write, it looks much cleaner, and the index I to which the Einstein summation convention applies is known as dummy index. So we have seen this scalar gradient. Now we can write it in a much more clearer manner. This one, right? So this shows the convenience, the avoiding too much of cluttering mathematics and notations, and this gives and we will use this Einstein summation convention in the next video to come. So, and obviously the value of I goes from 1 to 3 and so on. So that's it for today's video, and let us summarize quickly what we have learned. We have learned what are vectors, how basis of vectors changes, behaviors of vector fields, what is gradient, how and what is divergence of vector field, how we can use notation, how it helps, and the Einstein summation convention. So we will carry on with this mathematics of generality further into the next part. I hope that this video has been quite clear enough. You have got a fair idea about how these mathematics and things proceeds. Some very fundamental concepts like gradient of gradient and the divergence, vector field, basis of vector, and Einstein summation convention. Thank you for watching this video. Please do subscribe to my channel Physics for Students and like, and do let me know about your comments about this video, and I will wait for that comment and will be back very soon with much more interesting videos on my channel. Stay tuned. Till then, goodbye. Have a nice weekend ahead.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment, or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram, and LinkedIn. See you soon in the next video.